Okay, so our second speaker is Thiago from Brazil, and he'll talk about some factorized S-matrices. Okay, please.
Okay, thank you. Thank you very much. I start by thank you very much for the invitation. I visited your institute a few years ago. I have a very nice time. So I hope to visit again in the future. So I'm just having some. Let me. So okay. So now, can you see my screen or not?
No.
No. So okay. So just 1 second. Okay. Now. Okay, I think now it's okay. Now you can see my screen, no? Okay, so again, thank you very much for the invitation. So today the title of my talk is on factorizable S-matrix and generalized TTbar and the Hagedorn transition. It's based in my last paper, and I, of course, have to thank my collaborators in that work. So it's Giancarlo Camillo, Matt Lenz, Stefano Nego, and Sasha Zamolodkov. So the outline of my talk, I will start with some motivations and introduction. In this introduction, I will review some of the properties of the TTbar. Here in this talk, because I will define some generalized TTbar deformation, the usual TTbar, sometimes I will refer as a TTbar proper. So in these motivations, I will review some of the properties of this model, nice properties of this model. Then I will move for the rest of the talk. I will be only concerned with integrable theories. And they will define for you what I mean by this generalized TTbar deformation. So it's a class of some irrelevant deformations. And then to explore this theory, the main technique that I will use is the Thermodynamic Bethe Ansatz, that it's a technique integral for us. And I will use it to compute ground state, finite size ground state energies. And I will present results for many models that shows the same qualitative behavior of TTbar. So it has, for example, 2 branches that I will call primary and secondary branch. And then I went with my conclusions. And in fact, there are many open questions. There are many things still to be understood in this context. So okay, so let's move on to the introduction and motivation. So the TTbar that I call TTbar proper deformation is basically defined by this equation here that everybody is familiar, where the TTbar is this deformation. And we know that this is an irrelevant operator, but nevertheless, this theory is solvable in the sense that it's possible to compute many things in this theory in terms of the undeformed one. One result that is known is that the S-matrix of the model. So S0 here in the S-matrix would be the S-matrix of the undeformed theory. And when you turn on this deformation, what you get is this additional factor here. So this is the mass, basically, when you have just one particle. All the models I will consider here, it has just one stable particle. And I will set for the rest of the talk all the masses of the particle to 1. And when you see this S-matrix, it has some questions. So the questions are if there are other systems that have a similar qualitative behavior of this TTbar. And also many of the properties of this TTbar, I will review them a bit more in the next slides. For example, the Hagedorn transition, or this when we have all this relation with gravity and everything. Maybe it's when you look at this additional factor, you see that when theta goes to infinity, it has a very particular behavior. So maybe some of these features could be related to this behavior of this factor. But I show that it's possible to have systems with similar qualitative behavior without this growth of this special behavior of CBDs, of this deformation factor. So this was the motivation of the work. So, okay, so in conventional, so again, I'll say some words about TTbar proper, that will be important to understand, to compare with the other models that I present. So in a conventional relativist quantum field theory, we expect something like this. So I'll put the system in a cylinder, so I'll compactify this 2D space-time. And then you have some UV fixed point given by some conformal field theory and with some central charge. And this is the expected or conventional relativist quantum field theory with two fixed points under this flow. Then when you have this TTbar proper, the spectrum, it's known how to compute the deformed spectrum in terms of the undeformed theory. So I will just consider in the ground state here in the talk. So everything I will going to say it's about the ground state energy. So there is this relation.
Thiago?
Yes.
Can I just make one comment on your previous slide? I just find it a bit funny that you say conventional relativistic QFT and then you compactify space. I mean, that's, in relativity, of course, it's not very natural to have periodic space, right?
Sorry, I couldn't hear you well. So I'm very.
By conventional relativistic QFT.
Yeah, I'm just saying that you have a RG flow that you have two fixed points. So basically, this is what I mean by conventional here. So here you see when you put this TTbar, in fact, you have a very different behavior of the energy. So using this formula here, what you see, for example, there is two cases. There is a case depend on the size of this parameter. So basically, there is this case A that you see that in fact, if there is some maximum minimum value of R that you call R critical, and you see that you have two branches here. And here it's called the Hagedorn transition. You have a singularity here. That's called the Hagedorn transition. And for positive alpha, it's a bit different. You have a flow like this one. You have finite energy for when the R goes to 0. And in fact, this is also mysterious because you have a finite density of states and everything. So both behaviors are very unconventional, but in this talk, I will mainly focus in systems that are similar to this negative alpha, that they have a critical R. They have some you cannot go until the R equals 0 limit. So basically, this kind of theories, you have what I call primary branch, and there is a secondary branch. So this primary branch, in fact, it's possible to say that it's physical. For example, it's related with when you turn off this deformation, the system goes to this primary branch. But there is also the secondary branch that we don't call it unphysical, but we don't know the physical properties of this branch. But maybe there is some physical behind the secondary branch. So this is like an open question in TTbar proper and all the TTbar generalized that I'm going to tell. So in our work.
Can I have a question?
Yes.
So this the upper range in large R limit that is interpreted as a vacuum energy.
Oh,
right?
It's very hard for me to hear. So your microphone. Yeah, here this alpha, for example, if you take alpha equals to 0, I don't know if it was the question. If you have here, you have a behavior of 1 over alpha, so it's something singular. The secondary branch.
Thiago, can you hear me?
Yeah, I can hear you. Not very well. I could hear Alessandro very well, but I mean your mic I cannot.
Hold on, please. So the volume is too small, or how it sounds to you?
Hello.
Thiago, we can
Yes,
hear,
yes.
we can hear you well, but you cannot hear us.
Can you have both? What? I'm very sorry for this. I don't know if.
Thiago, can you hear us?
I think it's better now.
Oh, okay, okay. So I see microphone. So my question is, you have these two branches, and I
Yes.
asked upper branches in the IR limit, and this is energy is proportional to R. And
Yes.
This is a vacuum energy.
Yes, yes.
Now, in the lower branch, also in IR limit is also proportional to R.
Yeah. The leading it's proportional to R, and it's.
So this should be interpreted as some kind of vacuum energy.
Yes, it's some kind. Yes, but that is the leading is proportional to. Leading can be more complicated, but we don't know we know that the primary branch is related basically with the physics of the theory of the matrix of the virial theorem and everything. But the secondary branch is not related with turning off this deformation. So in fact, the physics of these branches is mysterious for us. I think it's an open problem. But yes, it's linear, but we can compute, but we don't know the physics behind it.
Yeah, something strange to me is that this epsilon usually depends on the original theory, which is
it's very mysterious because if you take this alpha to 0, you don't the original is give the primary branch. In fact, yeah, it's an open question. What is the physics behind the secondary branch? We don't know what system it is. If it is a different system of particles of the initial ones, what is it? It's completely open. At least to my knowledge, we don't know what it is. So okay, so basically I will say I have this you'll be focusing this negative alpha. I will show some system that has similar behavior of this negative alpha. So okay, so what is the generalized TTbar? Basically, I will now focus in integrable system. Integrable system has infinite conserved charges, and that is this higher spin conservations, conserved currents, local conserved currents. For example, in Sine-Gordon, it's possible to construct explicit this current. And it's possible to define operators very similar to the TTbar, which will be some higher spin generalization. There is some notation here. So fields with bars are related with some notations are related with fields with this kind of you have this map here. This is of the fields with bar, and then you can define now a new family of deformations that is triggered by this generalized TTbar. So this is what I mentioned by generalized TTbar. And it's possible to show that what happens when you turn on this generalized TTbar deformations, not only TT proper. It's known how the S-matrix change. So it changes by this factor here. That's proportional to this. It depends on this S. And basically, if you put S equals to 1, you return to the TTbar proper. So this will be like a generalization. And this factor is known as the CDD factor. So we start with some S-matrix in the undeformed of the theory, and you apply some CDD deformation. So the deformed theory in all the cases is still integrable. And basically the CDD factor satisfies some conditions like unitarity and crossing. And in fact, it has many bases. So the CDD factors, you can write in this basis here that is related with this previous discussion, but it's also possible to write in a completely different basis like this one. So it's just changing the basis. And here you have this part pole and this part entire. And what I'm going to study in this work are deformations of CDD that are given by this pole here. So you see that different, something that is interesting, it's that different from the TTbar deformation. This pole here have a nice behavior when theta goes to infinity. So it is not, it has a different behavior at infinity. So let's see if it have some behavior, if you have some qualitative similar behaviors of TTbar proper. So it's just a change of basis, but here we are just focusing this pole part in these different bases. So okay, I will use the TBA equation. So it's not to do some to compute the finite size ground state energy. So I will consider deformation. So we start with a free S-matrix that the bosonic case will be 1 and the fermionic case will be -1. And then I will multiply by these CDD deformations, right? And to compute this finite size ground state, I will use this technique that's Thermodynamic Bethe Ansatz that I'm not going to derive here. Basically, given the S-matrix of the system, you define some kernel and you solve this equation for this pseudo energy. And once the pseudo energy is known, you can compute the energy of the system. So the derivation can be found in books and reviews and also the original reference. But the idea is basically you have these integral equations here that when you solve, you get the ground state energy. It's possible to extend to not only to the ground state, but I will just focus the ground state in this talk. So given, so this is a technique to compute this finite ground state energy. And then I will show, for example, if you apply this TBA to the TTbar proper, we know the S-matrix, the exact S-matrix. And then this you will get some deformed kernel, right? And then you can use, for example, the TBA will be a different way of computing this, this finite size energy. And then what happens is this is the equation for this deformed theory, right? And then you use the expression for the deformed kernel here, you plug it here, and you see that in fact you get this equation here with a shift in this R piece here in the beginning of the equation. So then you get the usual expression for the energy, the ground state energy of the deformed theory with the undeformed theory. So this is just but now we are going to apply the TBA also for different system, and then we are mostly doing numerically. So okay, so what the models I will be considering in this talk? So I will be considering S-matrix deformed by the CDD factors here. So I start with some trivial S-matrix given by sigma here that corresponds to the fermionic and bosonic case. And then I will multiply several of the CDD factors. So I will deform this free S-matrix by CDD factors. And of course, these parameters here, UP here, are not completely general. So of course, there is the obvious periodicity of the sign here, but there is also one working assumption of our first exploration, that we are going to consider only models with a single particle, just one stable single particle. So we are not going to allow any pole in this S-matrix that will correspond to some bound state. So this is a work assumption. In the future, maybe it's possible to relax this assumption and study more general range of parameters. We know also that it has to satisfy many analytic requirements, and then we get the following models that will be considered. So there is the one CDD models. Basically, there is case A and B, and there is possibility of doing fermionic and bosonic case. So the case A and B are well-known cases. So the case A is the S-matrix of this Sine-Gord model. The case B is this star case model that I will say a bit more in a few slides. I will say a bit more about it. This star case model by Zamolodchikov. It's show a very nice behavior. I will show. And the bosonic version of these one CDD models have also been considered in the literature, beginning by this Musardo and Simon paper. And the two CDD model, you just have these cases here. You can classify in these different cases, different possible model, also fermionic and bosonic. Most of the results that I will show, the plots and the numerics, will be for this case D here. That basically you have these two parameters with one complex conjugate to the other. I'm showing just this case because we did the analysis for all the cases, A, B, C, and D. And so we did a complete analysis, but the results are qualitative the same. So I will show the results for D. It's very illustrative of the behavior of this system. So many of the results will be on the case D. And also, of course, it would be very nice to extend this work to the case of 3CDD, 4CDD, and so on, to see if many of the features that you mentioned, it's present in all these cases. But so we did some exploration of the 3CDD, but not a fully complete analysis yet. So let's start with a simplified limit of these models. I mentioned that I focus in this case D. Let's start by what we call the Nairo resonance limit. Basically, you take one of the parameters for the specific values, and this is nice because the kernel, usually a complicated function, it becomes two delta functions, and the TBA equations is easier. We're still not possible to solve it, but it is easier. And the Nairo resonance, because the model has resonance, and when you put this parameter, the resonance is very long-lived. So this is why we call the Nairo resonance limit. So the TBA here becomes a difference equation of this kind, where Y is, this is the definition of Y. So it's the beginning, so it's a different equation. Of course, it would be very nice to solve this equation completely. Maybe it's possible, but we haven't succeeded to solve this model completely. And one thing that we notice that only writing it in a nicer notation, you see that what appears in the right-hand side is this G that has this form here on the TBA. And once you move in this lattice, this G is exponential suppressed, right? And also, when you study the solution of the system numerically or try via truncations, you see that the y's are also exponentially suppressed. So it's possible to truncate the system to get some intuition on what is going on. So when you truncate the system, you get some results up to exponential corrections. Right? So for example, if I truncate the system for m equal 1, you have a very simple quadratic equation that you can solve. And again, what you see is precisely that there are two solutions that it's very similar to this TTbar property. It has the primary and the secondary branch. So here in this simple limit, I show the results for any kind of parameters. You already see that you have a primary and a secondary branch in a very very up to exponential corrected terms. So this graph is just a truncation. I show a truncation for m equals 1. You can do higher truncations, for example, m equals to 8. And then this plot is only to show, basically, that this narrow resonance limit, it's a smooth limit. So you can change the parameters of your model. And then what happens, you get some smooth limits to this narrow resonance limit. But there is still many things.
Sorry, this question. This that you're plotting is a numerical solution without any approximation?
Yeah, I'm truncating the system for this system for m equals 8. And then it becomes an algebraic equation. And then you can solve it exactly also for
and m equal 8 and m equal, I don't know, 20 is the same.
Yeah. In fact, m equal 8 is this dot lines here is the narrow resonance limit, but the other curves in the graph, it's numeric, it's not analytical. So you need to do the numerics that I show in the. So in fact, the only plot you get, it's the dot. So it's also very interesting the case with theta naught equals 0. Theta naught equals 0 is basically the position of these poles in the. And then you have some the bumps of the kernel are at theta equals to 0, and it becomes a very simple algebraic equation in this case that in fact you can solve and also do some expansions in theta naught and learn something, learn many things. But now we do the general cases that is solving the TBA. For different range of parameters. So this was a limiting case, only for us to see that even in this limiting case, you already see this behavior that you have a primary and secondary branch, there is some turning point, there is some maximum R. So now let's move to the general case for any values of the parameter. So the usual way, the TBA equations are very hard. So it's integral equations. It's very hard to solve it analytically, just for a few cases. And mostly, many of these, almost the applications is to solve it numerically. So by a method, an iterative method. So we start with some seeds, some solution, some initial guess. Usually here is just this driving term here. And then you see that after a few steps, this will converge to the solution of the TBA. So in practice, it's very efficient. We can compute usually the solution of this very efficient to almost arbitrary order. So to have some big, and there are also some theorems that proves that in some cases, the solution is unique and it exists. So several existence and in this case, in the fermionic case, the theorem that we know that maybe there are more, but that it says that the solution is unique and exists, converge, when the kernel, the norm of the kernel is basically less this one, if this integral is less or minus 1. Basically, this norm is counting the number of CDDs. So if you start with 2 CDDs, 3 CDDs, and everything, it's not In the theorem is only valid if the kernel has this property. And in fact, this is very nice because I will show that the models with one CDD, it's have just one branch, just one the iterative branch. There is no this secondary branch or this Hagedorn transition. So I will show some celebrate models to you. So there is this star case model that I say that is it's one CDD fermionic by Zamolodchikov. And what happens is that when you run this CDD, this TBA and compute the ground state energy, what is going on is when you start to decrease the energy, the iterative procedure always converge. When it has some limiting R, it stops converging. When there is this, it stops at some R. I forgot to mention in the last slide, there was this last comment. So in many cases, when you apply these iterative solutions, what happens is that it stops converging for some values of R. It becomes very slow and then stop converging for some values of R. And these are two cases that you can take R up to 0. So it's the TBA always converge, this iterative procedure. So there is this star case model that is one CDD. And you see this plateau here. The system is moving as these conformal minimal models here. And there is also example with higher number of CDDs. There is this work by Martins that basically have 3 CDDs with this parameter, and you see precisely the same behavior. I'm not very familiar with this minimal model that considered by Martin, but I just want to show that this TBA goes up to R equals to 0, the iterative procedure. You have just this one branch. So, okay, so generically for other models, what happens is this iterative procedure stop converging for some value, finite value of R. And what happens is that there is 2 branches because the singularity is of the square root type. So here in this plot, I show all the models that we consider. So you see that there are some models. This is the plot for the ground state and energy in terms of R. You see that there are some models that converge for any R, but the others, for example, it's even TTbar here is this black. It stops for some R critical. And it's possible to fit the behavior close to this R critical and see that it of the type of square root type. We don't have an analytic proof that it's always the case, the square root, but in all the cases that we investigate, you see here the plots. When it's square root, this inverse of the derivative is some line here. So it's very convincing that in fact you have these 2 branches.
Can I ask a question?
May I ask a question?
Yeah.
So for the R star, do we have any analytical understanding, or you can only find it numerically?
Only find for this apart from TTbar, it's like numerically. We don't know the value of R critical. We get some guesses from the plots, but we don't have an analytic expression for it.
Mm-hmm.
So okay,
I also had a question, if that's all right.
Yeah.
So this calculation, you do it like in theta space. This because I have this memory that sometimes these sort of calculations actually converge or are more manageable in the Fourier transform, right? Instead of doing the convolution, you do a product. I don't know. Is it something that you looked at?
Yeah, it's always that space. It's in the iterative converging. Yeah, we did some. This maximum R will be present in any case, right? So you have this maximum R. But for example, for the bosonic case, if you use this iterative method and you go below this maximum R, in fact, it converges, but it gives some complex solution. So it can depend on how you treat this iterative. You can get some result, and then this value of R star will be always the same.
And you discretize the theta value, or is it
Yeah, discretize the theta value. Yeah, it's discretize the integral. So now I will show a method that, in fact, here is the iterative one. In fact, it's possible to plot, to have some plots like this one, that we start in the primary branch and then you go to the secondary branch. So the iterative solution does not give the solution of the secondary branch, only the primary one, but there is a method to go, to follow the curve, to follow the solution of the TBA, and then move from the primary branch to the secondary branch. So the method, it's known from some mathematician and we adapted here. Basically, we have a problem that you have like turning points that you move to the R and then you have to go back because you have a maximum R. It's possible to have problem with bifurcations that you start with some branch and it becomes two, but here in this case, all the cases are just turning points, and this way it's just related to what I'm going to say. It's for turning points, not I'm not considering possible bifurcations. So the idea, basically, I just flash the details. What you want to do, we start with some function h that basically is the TBA equation with some discretized theta grid, right? And when this function is zero, it's basically gives you the solution of the TBA, right? And what we want to do is basically follows the solutions of TBA along a curve, right? Along a curve. So we want a curve that is in the kernel of this functional h. So given a starting point and a final one, we want to find a curve that in every point is the solution of this TBA equations. So because you have this divergence in R, the first thing to do is to write a nice parametrization. So instead of taking R as parameter, now the initial trick is to take all the variables, also S, depending in a good parameterization. That you call the arc length because we impose some normalization condition here. So then how the code works, basically we start with some point, we move, you do a guess of the next point. That works very well infinitesimally, so you move in this curve with some guess. And then, but usually when you do this movement, you are not proper in the curve, so you have to correct a bit the result to move to the curve. So basically you do some prediction and correction, prediction and corrections. And the predictions, you just move in this way. And the correction it's a bit the trick part. It's because now this h, because all the parameters now depend on S, you have some non-square matrix. And then you have some to adapt Newton's methods to get this corrected, and there is some way of doing this. So there is this way, and with this analytic continuation, we can plot this very nice graphs here. So we start in this primary branch, and then you move to the secondary branch, following a solution of the TBA equation. So this primary branch, it has this behavior here, and I will show that the secondary branch has, as was the question, it is also linear in the limit. So we got this kind of graphs here.
Can you move backward?
Sorry?
You start from the secondary branch.
Yeah.
And increase this value of arc, size of arc, S variable. To go
yeah, you can do. You given an initial condition, you can move in the solution, the curve solution. So if you start in the secondary branch, you can go backwards and move to the primary one.
How do you define the initial condition? How do you distinguish the primary branch or secondary branch?
Because usually to go to the secondary branch, we don't know a different method to get the secondary branch solution. So we start with the point that the solution using the iterative method. So we need to start from a solution. So the way we solve it in the primary branch that we know via iterative procedure, and then given a solution, we can move in the curve. But if you know another way of solving this TBA in the secondary branch and giving me a starting point, then you can move backwards. So it's just because we don't know how to solve the TBA in a different way for the secondary branch. So this is why we start in the primary one. So, okay, so I will show now several results, and we almost have zero analytic understanding of these things, but there is one thing that it's possible to understand analytically, that is the large R behavior of the solution. So this is possible to understand analytically. And the argument is because given the TBA equation here, when R goes to infinity, is to see that this driving terms increases with R, right? So for this equation to have a possible solution, we need that or this pseudo rapidity here or the convolution, they have also to behave as R to compensate for this growing, right? So just analyze how the terms behaves at a large R. We can understand the large R behaviors of the solution. So there is this case one that is related with this primary branch, that is the usual one. So in the usual one, what happens is that this convolution term is very small, and the pseudo rapidity one is growing like the driving term. So this is consistent, and it's a possible large R behavior, and you know that this is like the primary one. But there is a case two that we have these ansatz here, that in fact this pseudo rapidity has different signs in different regions. So there is a region of positive pseudo rapidity and regions with negative pseudo rapidities. And it's also possible, in this case, the convolution term, it's also big, it's not being suppressed in the large R. And then you see, if you put this in the TBA equation, you get some equation for this F. Basically, this is the condition that this secondary large R behavior exists if this F satisfies this equation here. So we can analyze this equation and see some conditions for this F to exist. And in all the cases that we analyze, in fact, it's possible to have this second solution. So basically, what is the trick is that this pseudo energy has a negative region, as I'm going to show in the next graphs.
May I ask a question here?
Yeah.
Sure. So in the proper TTbar, it is well known that it's an irrelevant deformation, so it doesn't change much the R goes to infinity limit. Well, in this generalized CDD kind of deformation, is it clear whether it's an irrelevant deformation or is a mixture of irrelevant and relevant, so it changes both small r and large R?
Yeah, just all these irrelevant ones, they are irrelevant. All these generalized ones, they are irrelevant, are TTbar. And basically, you have the way you have when you plug these deformations, all these deformations, you construct the full parameter of CDDs that I show in the beginning. Yes. And then basically what I'm saying, I'm expressing the CDDs in a different basis only. Okay. So I can explain just deformations in terms of the original one. So, okay, so here we have the case two. This is the way I know. Maybe there is a clever way of considering this map. Okay, so there is some numeric. Yeah.
This argument that you're giving, or this observation that the pseudo energy becomes negative. This is for fermionic theories or also for bosonic theories?
For fermionic theories.
Stability, right?
No, it's fermionic here. I mean, the plots are for fermionics as well. And then I will say how to relate to the two, and you see that in fact what happens is that in the bosonic case, you don't have this negative one, but
I mean, otherwise the log would become imaginary, essentially.
Yeah, precisely. So it's okay. So here I'm showing the numeric results for the fermionic ones. And for large R, here R equals 5. So for some range of the models, R equals 5 is already big R. And you see there is this region, this negative region here for the secondary branch, and the primary branch is always positive. There are many questions because the number of regions of negative epsilons can be, we don't know why it's just one. It in principle could be many. So we couldn't prove that there is just one region. And also the size of this interval. It would be very nice to understand the size of this interval of negative R, that we also only know numerics, that some properties of it. But this is general for all the cases, and this is the expected behavior. And now close to R, we can plot this L, that is basically this log that go in the convolution of the TTbar. And you also using this analytic continuation model, whether you can move from primary to secondary branch. And here you see that the L for the secondary branch is always bigger than the primary one. This is basically implies that the secondary branch has a lower energy. So this is always the case. The secondary branch has always a lower energy. You see from this graph here. And also you can plot the dependence on on the critical R with the parameters of the model. So basically here this X, basically it appeared in a graph, but the definition is the logarithm of R over 2. And you can just do numerics and see how it changes with the parameters of the model. So one question that is very nice to answer is, you have this R critical, right? This minimal R, but in principle, it depends on the model itself and the parameters on the model, but it could, in principle, depend on theta as well, right? So we did some numerical investigation that maybe it's possible to do some analytic investigation, that in fact, for all values of theta, with doing a nonlinear fit, we get the same critical R. So the critical R is independent of theta, and this is a feature also of TTbar proper. So this is something nice as well. So it's the same qualitative behavior here. So a comment about the bosonic case, as Alessandro already asked it as well. There is some complications in the bosonic case, but about the numerics. What happens is when you use this analytic continuation method to the bosonic case, it starts in the primary and goes to the secondary branch, but then it jumps back to the primary branch. So it's very unstable numerically. And basically, when you plot these functions in the theta plane, you see that there are some zeros of these logs approaching the real axis. So this is causing this numerical stability that we were observing numerically. The way to solve it is basically to map a fermionic and bosonic TBA equations to the fermionic ones. So this map is well known. So if you have some solutions of the bosonic TBA equation, if you define this pseudo energy tilde here, you'll be a solution of a fermionic TBA equation, but with a different kernel. The kernel will be the bosonic one times these corrections with a delta function. So basically, this is a solution, and this implies basically that a bosonic NCDD model will be equivalent to n plus 1 CDD fermionic TBA model, because this delta here can be obtained from the CDD expression by taking some limit, so imposing this limit in the parameter. So basically, when you move from the bosonic to the fermionic, you see you have this map, and so it's enough to understand this fermionic TBA. And in fact, the fermionic TBA is it's trivial in sense that you can go to the limit r equals 0 for the 1 CDD case, but the bosonic case, it's already non-trivial for 1 CDD because the 1 CDD bosonic case is related to 2 CDD fermionic case. So I have just a few minutes, but it's my last slide. So so the conclusions and open problems. So one of the questions, of course, it's one of the main open questions for this kind of deformations of the and also TTBR property. What is this physics behind of the secondary branch? The primary branch is related to the S-matrix, to the particles, to the physics of the model, but the secondary branch, maybe there is some interesting physics behind it, but we don't know. Also be very interesting to understand what's going on for R below this critical R. The energy become complex and maybe there is some decay, but we don't know what will be the product of this decay. And I think one of the main motivations of the work will be like these physical conditions for the formation of the singularity, because it was one of the expectations was that the singularity would form because you have this exponential, very special deformation of the S-matrix that has some special behavior of at high for infinite values of theta. But here we show that for the simple CDD, there is no strange behavior of large theta. You also see the formation of the singularity. So I think this is the main, maybe the formation of the singularity and the understand of the singularity is more intricate, it's more general and more intricate. But we still also do not understand the physics. And of course, we had many numerical results, but it's possible to do many analytics. I think many things can be deduced analytically. And also you consider just this pole part of CDDs, you can include this entire part, play with more general case, with more different types of particles, also consider the massless case, maybe something new appear. So there are many open questions, many future directions, and I stop here by thank you very much for the invitation, for the opportunity, and financial support of the Serra Pileira and the Associação Instituto Internacional de Física. So thank you very much.
Thank you, Thiago.
So may I ask a question just to clarify, I understand?
Yeah,
so,
yes, please.
For the 1 CDD, the TBA is fine. And for 2 CDD, you have a second branch. Is it correct? And what about like 3 CDD? Is it also a branch or is something more exotic?
Yeah, there are some cases, for example, of this model of Martin here, that it's 3 CDD and you have just one branch, a finite one. So the expectation is, in fact, we have some islands that we have this normal behavior, and some cases that we have these 2 branches. But for the great majority of parameters in 3 CDDs, we have this primary and secondary branch, but there are some exceptions. There is some islands that would be nice to. But the claim is that the majority of the models, the great majority of the models, have this behavior that we had we did some research about the 3 CDDs, but it would be nice to have also some analytical understanding of general CDDs. If you put 3, 4, and which cases we have the necessity. I mean, you'll be basically that question: what is necessary for the formation of the singularity? Basically, you'll be answered this question.
Actually, it depends on the parameters. Sometimes it's okay, sometimes it's pathologic. Is that?
Yeah, yes.
Okay.
And the claim is that the majority of the parameters is bad. You have a maximum R, but it's of course it's a preliminary. We did a preliminary studies of 3 CDDs. we plan to investigate higher CDDs and see what we get. But there is many things to do already. It's still.
Related to that, so suppose I start with a St. Gordon, and then I do a 1 CDD deformation. So then the S matrix, do I understand then it's like a 2 CDD thing, and if it has pathology?
Yes. In fact, what we did, we can start with some non-trivial S matrix, some non-trivial model, I don't know, and do the CDD deformation. So it will be basically or 2 or any. It's basically considered this entire part of this thing. So you can also do more general things, more explorations. But so this is maybe in the things for the future to explore the more general case.
Okay, thanks.
But we expect that this numerical analytic continuation will be valid for it to be useful to study any case that have this turning point. So it will be applicable to all cases. And yes, this is yeah.
Okay, that's very nice. Thanks.
Okay, thank you.
I have one question that, some of these early models, they're interpreted as string theories, like just so here, if there really is a short resistance R star, and you can't really resolve it beyond what you've done, I mean, does this mean these are string theories? I mean, you probably have Hagedorn. Well, you have Hagedorn in your title, so presumably there's some kind of, you're interpreting this as a Hagedorn transition, but I mean, are these all string theories somehow, or what?
Yes. That is just this is common to string theories, and in fact, if you take this phase here, so here you see that because it grows very rapidly for theta goes to infinity, it will imply a huge density of states, of 2-particle states and higher multiple states. So you expect some kind of Hagedorn transition for here when you have this growing. When you don't have this growing, you still have this formation of the singularity, but you don't know precisely the physics of it because it behaves, it does not seem to give a super strong, apparently, but it has some super strong growth of states. But yeah, the expectation is that it's still to understand what's the reason. I think here the reason is more clear. It's because of this growing of infinity, we can argue that the number of states are exploding. But in this other case, I think it's more mysterious. And this was basically the motivation of the work, to see that it's something similar happens with a nice behavior at infinity, with a more usual number of particles. And but the expectation will be string theories or maybe something that we don't know, but then we don't know. It's maybe there are some surprises.
I have a question. So can you construct some kind of ordinary TBA equation which limits the secondary branch?
If I can solve the TBA equations for the secondary branch directly.
Directly.
So,
and using some iterative method to generate the secondary branch.
Yeah, this will be great. We couldn't manage to do this. So if you try the iterative one, even if you start very close to the solution, when you know the solution, you put some gas very close, it is not the iterative methods go away and converge to the first branch. So we couldn't manage to find a way of solving the equation directly in the second branch. This will be something nice to do. And what we did was to follow the curve, to start in the solution that we know and move to the secondary branch. So with the method of this analytic continuation. But I agree. So it was something that we tried to start with very close to the secondary branch solution and see what happens, some iterative solution. In fact, there is something that that works in this way. If you have a very good guess, very good guess, for example, you see there is in Mathematica there is a function like find the root. If you have a nice guess, it will go to the solution, the find root. So this function find the root, but you have to be a very nice guess. So it's very close to the solution. So if you have a nice guess, I think that is a way. But the problem is to have this guess. So usually we don't know a good guess.
But to generate this IR behavior of the secondary branch, you assumed this logarithmic term, this kernel, to satisfy certain well-defined conditions.
You mean the larger behavior of secondary branch? It's
larger behavior. So if you find certain conditions of this kernel.
Yeah. So if you go, for example, there is this solution here for F that you know how the pseudo energy behaves. So you can try to solve these equations first and get a guess for large R, and then it will converge. But yeah, something that we don't know about this equation, as I mentioned, if you look at the solution, we don't know why it has just one interval. Maybe it could have many intervals that we have negative ones. And we have no idea what is the size of the interval is. So what is, maybe there is with some analytical work, it's possible to answer this question and get some nice guess and even solve the solution in general, something. But something that we leave for the future. We don't know the answers now.
I have a couple of questions, if I may.
Yeah, please listen.
So the first one is just to understand the statement. So you look for theories that have one particle, an S-matrix which satisfies crossing, unitarity, as proposed in the physical strip, and decays, or the logarithm of the S-matrix decays fast enough for larger values of the rapidity. And most of those you say are actually not local quantum field theories.
Yes, you have this Hagedorn transition and like this. Yeah.
But it's not possible a priori to know which ones are and which one are. I mean, if I just write an S matrix and I show you an S matrix, you're not a priori able to tell me whether it's good or bad.
No. This is nice, very nice question and open question. You'll be, in fact, to understand the physics of the singularity. You give me an S matrix and I can tell you if the singularity is formed or not. So this is completely open.
Related to that, it seems
the only one question is just working with one particle was like working assumptions. You can try to do more complicated with more particles and then apply the same methods and see what happens. So it's maybe for the future as well to consider more general cases.
So slightly related to this, it seemed that in the points, if you show the plot of epsilon as a function of theta for various r, right? So it almost looks like that at the transition point, you get something that has maybe like a higher order minimum, rather than instead of the second derivative being non-zero, the second derivative is actually 0, but I don't know, it's like it goes like x to the fourth or something like that. It looks flatter, that's what I want to say, right? Graphically. So at the threshold between the red and the blue lines, right? It looks very flat, the curve. And I wonder whether you have tried to study like the second derivative of the TBA equations or something like that to see that something might become particularly my signal transition if those equations for the second derivative have a 0, say, as a function of theta.
No.
Second derivative with respect to r.
Yeah, we haven't done this analysis. The first derivative will be singular, right? But the second we haven't explored. I don't know.
I mean, it's yeah, I don't know. It seems like I mean, also as a function of theta, it seems that these things have some particular type of singularity. That's what I wanted to say.
No, okay, yeah, we haven't explored these higher derivatives and of the TV.
Thanks.
I cannot say anything at this moment.
Just out of curiosity, maybe it's a hard question. So if you see these pathologies in the spectrum, probably you should also see it in correlation functions. Say if you use form factor to compute correlation functions, then for these values which you have problem with the spectrum, maybe the convergence of the form factor should also be problematic. So is there any way also to see this kind of singular behavior for correlation functions? That's my question, because now your CDD factor is better behaved. So in principle, solving the form factor axiom should be easier, or should be less problematic. And in principle, one can push a little bit and see if you can see something in the correlation function side.
Yeah, I think it's a very interesting question, but yeah.
This R is the size of time direction, and you are probably talking about the spatial distance between two operators.
Yeah, but I think in any case, this is a UV type of singularity. You should see it anyway, right?
Right. So, but this is a kind of temperature, right? So it's some correlation function of the finite temperature theory.
But you can do just rotation.
You can do some rotation.
Yeah.
That's true. But somehow this compactor expansion is valid when this scattering theory is well defined. Infinite zero temperature theory.
Yeah, I couldn't hear the end, but
What I said is that compactor expansion of the correlation function is usually valid for the zero temperature theory, where scattering theory is well defined.
So I have some difficulty to hear from.
I'm sorry, so we have another problem.
Yeah.
But you can you hear us in other place?
Also in a very blur way. It's not completely clear.
So our internet situation here is not so good. We apologize.
Maybe it's related to the microphone or something. When you speak, we can hear a very weak voice. And
Yes. Yes. But I mean, the conclusion is we haven't explored correlation function, but I agree it's a very nice direction to go and see this kind from this point of view. But yeah, we haven't explored yet.
So, is there any other questions? Okay, so it seems not. So let's thank Thiago again.
Thank you very much. Thank you very much for the invitation. Okay.
So this will be the end of the morning session. And somebody, do you have any?
Okay. Bye.
Bye.
Thank you, Thiago.
Bye.
So next session will be starts at 4:30 in Korean time. So And then tonight we have also panel session at 8 p.m. in Korean time. So, yeah, see you in the panel session. Yeah, fine. Thank you. So lunch will be ready at 11:30. Yeah, in 4 minutes. So we can pick up the lunch box and officially I would say you have to eat the lunch box in your room.